And this is precisely the topic of our next session, AIML applications for robotics. And the speaker of this talk is Mr. Vijay Seelam. It is my pleasure to introduce Mr. Vijay. Mr. Vijay Seelam is a serial entrepreneur with more than 25 years of experience in starting and leading deep technology companies. He founded Svaya Robotics with a mission to bring human-centered robots to help shape new production landscape that are adaptive, data-driven, and retrospective. Under his able leadership, Svaya has developed India's first collaborative robotic platform with pioneering advances in zero-code human-robot interaction, safety, advanced robotic perception, and adaptive workflows driven by AI/ML. Prior to Svaya, he founded Zuti Engineering Solution and shaped it to be a leading provider of end-to-end solutions in development of highly engineered product and integrated manufacturing to help enterprise realize their business visions. Vijay started out as a product development engineer at Ford Motor Company in Michigan. After that, at Altair USA, he was a worldwide product line manager for optimization and CAE analysis products. Subsequently, he was director of business development for Southeast Asia at Altair. He holds a master's degree in mechanical engineering from University of Florida, Gainesville, USA. With that, I welcome Mr. Vijay Seelam for your presentations.
Thank you, Kamal, for your kind introduction. So I'll just bring up my share screen. Okay. It's okay. Yeah. Can you see my screen?
Yes, we can see your screen. You can put in the
Great.
slideshow mode.
Good afternoon, everybody, and thank you, Kamal, very much for your kind introduction. So, as you said, and at the outset, thanks to IESA for giving me this opportunity to talk this occasion. So we had a lot of, I've attended a couple of sessions in the morning, excellent perspectives and presentations, and also in the last 1 hour, a lot of demos. And looks like machine vision is almost synonymous with artificial intelligence now. So my presentation is going to be slightly a little bit different. We have seen a lot of automotive applications, but we are going to talk and focus more on industrial robotics. We feel like industrial robotics is a prime candidate, the combination of robotics and artificial intelligence to really transform the, especially the manufacturing industry, if you will.
Mr. Vijay, sorry to disturb you. Can you put your presentation in the slideshow mode, presentation mode?
Yes.
That would be great. Thank you so much. Yeah, now all good.
Great. Thank you. So I just want to give you a little bit of an historical perspective and where we are coming from and where we are heading to. Apparently, 2021 happens to be the 100th anniversary since the word robot was first coined by the Czech playwright Karel Čapek. And as you know, it was played, it was called Rosum Universal Robots, staged in 1921 in Prague. And you know, the rest is history. The reason I'm saying this, until 1961, we didn't have anything called a physical robot. And the first robot was Unimate, and it didn't look anything like Apex robots. As you can see on the picture on the right, it's basically robotics has come to mean more as impersonating humans or taking human form, and a lot of negative connotations with it, especially when it comes to like employment and taking away the employment and all that. Okay, so now the question is, how can this industry transform, and where we and what the industry looks like today? So most of the industrial robots are out there in some of the very mature industries like automotive, semiconductors, or like a clean room kind of manufacturing operations. And they're predominantly like caged behind safety fences because they're not safe to intermingle with people, or people are not allowed to go besides them because they're huge and they're not completely safe. So they're basically deployed for hard routine work, but they're not smart by any rudimentary sense, if you will. And one of the biggest barriers for wide adoption of robotics in other industries, other than automotive, semiconductors, and few others, has been one, they have not been very adaptable, and they needed experts to program and operate them. And then safety is also one of the biggest concerns. And they needed highly structured environments to get them going. So when I say highly structured, everything had to be pre-planned and laid out. So any small disruption anywhere in the production line, the robots just would come to stall, and then you would stop the entire production line. So, but that is expected, like, in a mass producing industry like automotive and semiconductors, but not so in other industries, which are more discrete in nature, and a lot of flexibility and adaptivity is needed. So now the question is, can we graduate robots to work alongside people? Because this is the need of the hour, especially in a lot of industries, because we don't believe that the robots are going to take away people's jobs. So it has to be a mix and match of both, to use the ingenuity and creativity of people and combine it with the precision and the reliability of the robots. So can we transform them from utilitarian to augmenting smart collaborators to human beings? And now, Svaya, we have started this company on this premise, and we definitely believe the advances in artificial intelligence can make a transformative changes, especially in robotics. And we can bring about to connect people, process, and purpose to make the manufacturing environments, or wherever the robots are deployed in different environments, to be more adaptable, data-driven, and responsive. Svaya is a full stack company, and our platform, we call it Unrestricted Robotics. And the reason we say that, we have, you contrast this to the current industrial robots, which are one, very expensive, and which take a lot of expertise to program them and deploy them, and then a lot of bells and whistles go around them to really make them work. So your production line, the entire production line has to be planned and structured. But in contrast, what we are saying is, we can have these robots like, especially the human scale automation, we call it like 1 kg to 20 kg payload robots, typically where human beings are deployed and work. Okay, the payload may not be an issue, but definitely it could be an occupational hazard if you're doing repetitive work. And in today's world, as your education levels are increasing, you have a challenge of finding the skilled people wanting to work in manufacturing, especially the dull, dirty, and dangerous jobs. And you need something to take over this. And these robots, you can just unbox them, and within 1 or 2 hours, you can get them to deploy for automation of simple tasks. And this essentially relieves the human worker for essential work or more creative work. And then comes like, how we can mix and match with people, and where we can augment the people, where people are used for more creative and thinking jobs, as I said before, and the robots can be deployed for more precision and reliability, where we can increase the combined productivity of people and robotics. And our the Svaya's unrestricted robotics platform is completely ready for autonomy. We have, and in the future, it's going to be more and more software driven from the virtual space rather than you deploy the hardware once, but it's essentially software is what is going to drive the automation or the robots. And now that's so much for Svaya. I just would like to focus on the artificial intelligence, the challenges and the applications in the industrial robotics area. So the three main challenges as you come across in industrial or warehouse robotics. One is understanding the environment around it, which we call the ambient intelligence. So the robots need to know what's going around them. And then the contextual intelligence, which are how things are changing dynamically around the robots and what do they do with it. And third one is the task intelligence, which is more intrinsic and intimate understanding of the task at hand and how they can get better at it. And the ambient intelligence or the understanding of the environment around the robots is a pretty well understood problem. And in the last 10 years, there have been a lot of companies which have been designing robots and also applying a lot of advances in machine vision in warehouse kind of applications, or even in service sectors. The contextual intelligence problem is a little bit a tough one to crack because this is what human beings are very good at. Even the robots, even as we speak, they don't come any close to even a small kid because this is a very innate nature of what is to be a human. So we pursue things very quickly, but the robots have to be told explicitly. Now, can artificial intelligence and machine learning, the advances in there can change, can this change? Because if it changes, this can open up huge application areas to penetrate for robotics into. The third one is the task intelligence, which is, if you take one example in the industrial area, the understanding of the geometry of the task, essentially the features, the color, the size, grade, and things like that. Some advances have been made there, but still there's quite a bit of work that needs to be done. And as you could see, like from what I said just now, the implication is that these models have humanistic learning features. See, more like how humans learn about things. So it's not necessarily us as adults, but if you have somebody starting out in a kindergarten, right? So one is the communication, and then you learn more as you get more experience and you keep practicing. And if we have to apply artificial intelligence or machine learning in robotics, and they're not going to be any different, but with different nuances and different flavors of it. Now, the four pillars or the framework for implementing or application of AI in robotics, as we see it, is one is the problem of sensing, then the perception, then the decision and policy, and then finally the execution through the robot. See, at the end of the day, robot is a physical manifestation of what you think in the virtual space, and which could be your artificial intelligence or machine learning, and how we are going to deploy that and get things executed in the physical space. So through this, we can make or physical actions more and more intelligent. So now the sensing, we have heard a lot of presentation, nice presentation about edge computing, and definitely this is quite relevant, and this can make a lot of things applied in robotics, especially the sensing, because one, you have the sensors inbuilt into the robots, like your vision, or it could be your encoders or proprioceptive sensors like your accelerometers, gyroscopes, and things like that. And then you also because robot is not an entity that's going to work by itself, especially if you're talking about the industrial environments, because they have to coordinate with other machines or with the rest of the ecosystem. So, which obviously implies that there are going to be other sensors which it has to talk to and get data from, right? Or it's a bidirectional or a multi-directional communication, because there are a lot of agents involved in this environment. So now in the perception, you need some kind of a sensor fusion where we are going to integrate this data both from the inbuilt robots and also the ecosystem. And we can bring about a comprehensive awareness or understanding about the environment to the robot. And if anything is changing in the dynamic environment, we can pass on the cues to or the robot will notice the cues, right? So that it can plan its motion or actions in real time. And later, I think we'll show with a couple of applications how this is going to be. And then once you have the perception, obviously you need a decision model or the mental models of the robot of how it's going to assess the motion or plan the maneuvering. And also when we're talking about robots getting involved or intermixed with people, safety becomes a very important issue, and there are a lot of regulations here. So obviously these all have to be complied and built into the models. So which is basically the policy, if you will. And then the robots may be working along with other robots, and they need to coordinate with each other. And then finally, the execution. So you need to execute this decision through the robot's actions. Now, although we are saying like, the electronics and the technology sector is concentrating more on the artificial intelligence, machine vision, and a lot of edge computing or cloud computing, and a lot of this kind of technologies. But the robot we see right in the physical space is a complete old product, and they are completely interrelated to each other, because how robots are constructed, their kinematics and all those also matter to make some things possible, and some things could be hindered because the way things are done in the physical robots. Now, as you see here, the sensing is definitely, I think, edge computing can bring about a lot of changes here, especially in the robotic vision, and also, especially when we are talking about a large factory and we have to coordinate among several robots. And we also want to know what is the trending data in the production line so that we can make it more data-driven and more objective. And the robot also seeing the data, learning from the data, and getting better and better every day. So edge computing becomes very important. And then of course, there's some challenges here, how we are going to integrate, because the form factor is a very important issue. And then for the sensor fusion, so partly can it be done on the edge for simpler applications, or probably we have to go to cloud for, especially for perception or sensor fusion with integrating the data from the robot sensors with the environmental sensors. And then of course the decision and policy making, are we going to do this like the decision models constructed in the cloud, or dedicated computers which are tethered to the robot? And tethering the computing device to the robot is also a restriction itself. But in the industrial sector, we have what is called deterministic communication, because you don't have your regular Ethernet and all that, but we have more like field bus kind of communications like EtherCAT, Modbus, DeviceNet, Profinet, because you can't use Ethernet IP as it is, because you're sending the packets, and sometimes the difference between life and death can be a split second. So you can't afford that there. But with the 5G technology and wireless communication, the expectation is that it's going to be a lot more reliable, and this can unchain or cut the umbilical cord from the robot to the master controller, and it can communicate in the cloud. So that can remove a lot of restrictions of how the robots can be deployed. And now coming to some of the applications, one of the challenges is object detection, and AI and machine vision especially can play a big role. Apart from, here the basic challenge is, one is obstacle avoidance, especially if we want the robots to be working in human-infested or human-centric environments, or they're coordinating with other robots. And more so if the workspaces are unstructured. So let me say, qualify this. When we say structured, everything is planned and everything is deployed as per the plan. But in unstructured environment, things could be not necessarily planned. They could be say, for example, a fixture could be slightly oriented differently. But if you can tackle this problem of allowing the fixtures or the objects to be placed slightly different and not necessarily creating specialized fixtures to position them accurately, right? This can remove a lot of barriers, although this sounds very trivial, but it's a big deal actually. So this can make robots even more, much more adaptable, especially in SMEs, small and mid-sized companies. So obstacle avoidance. So yeah, you have your humans and other robots, and if they're moving into your space, then how does the robot recognize that and then come up with an alternative plan so that the robot and the people are completely safe. Then shape and size is another different challenge altogether. Again, this looks very trivial even for an infant. You can handle it very easily, but for a robot, it's not that easy. And then other thing is, especially in a dynamic environment, things are moving, the approach and time of flight, all these things become an issue. So, so there's a lot of learning and learning models, and especially the computer vision and artificial intelligence can have a huge impact in coming up with new applications in this area. And one more application is the manipulation, if you will, the fine tuning, the final process of the robot acting on its action. Like say, for example, gripping. What is the gripping strategy based on the size, shape, orientation, or even the texture, right? So as you can see on the left-hand side, the shape of the object has to be known for the robot to plan its gripping strategy. So for example, if you have some kind of a pyramid shape and if you hold it at the tip, then it's going to fall off. So that is something that it has to become cognizant of. Then on the right-hand side, you see there is a flask with a glass flask with water. Obviously, it has to be handled more sensitively. If you apply excess force, then it's going to break. Then you have a lot of different kind of permutations and combinations in the industrial area, where you have soft materials and then they're juxtaposed with hard materials. So we need to know how much force is applied and how they have to be oriented and fixed with each other. Then, and more recently, especially in the light assembly, if you will, like in electronics applications or assembly in cell phones, or even a lot of other electronic assembly applications. You have we need tactile sensing, because these are very sensitive parts, especially if you are inserting some of these parts onto the PCB, the connectors and things like that. If you apply excess force, then the parts are going to break. So you have something called tactile sensing incorporated into the robot, especially in the end effectors, if you will. So they basically give you a force feedback or a torque feedback, and basically based on that, the robot can adjust itself. And we teach the robot with several, multiple examples, and then it can start learning a little bit about the properties of the material, and it can act accordingly whenever it sees or faces that. And another good example is when we are doing a complex assembly like a gear, because as you can see here on the right-hand side, we are trying to assemble a gear. This can be a very trivial thing for a human being, but for a robot, because if it's not going to slide in perfectly, then you might end up damaging the parts. So here we have what is called a wiggling, and the wiggling is based on tactile sensing. It has to sense forces in all the 6 directions so that the part gets inserted correctly without damaging the assembly. And a lot of applications on inspection, especially with machine vision and artificial intelligence. The companies which are implementing this as a standalone product, but this can also be done with robots, especially if you want to implement in-process quality control rather than you produce it and take it to the quality room and do the checking there. So this can save a lot of money and a lot of time for manufacturers. So especially the defect identification, you have the parts, and if there's a certain part that has not been assembled properly, or like there was a defect during the manufacturing assembly part process, how do you detect that? And if you detect in process, then probably we can stop the assembly line and prevent other similar kind of damages happening for other parts, and you can end up saving a lot of money. Otherwise, it could become a costly affair, which we see all the time. And today, even
can I request you to conclude in the next 2 minutes, please?
Yes, yeah.
Thank you so much.
Yes. And then surface quality is another thing. And then functional verification, as you could see in the middle video, like where we are using the tactile sensing, we are trying to verify the capacitive touchscreen of a tag. And you can see here, you have to apply gent wash depending on whether it's a glass or what kind of material it is. And so you have also can detect missing parts in the, especially in complex assemblies like PCBs and all that. Now, this is my last slide. Just to conclude here, as you can see here, artificial intelligence has the potential to make robots as ubiquitous as personal computers in our lives. We wouldn't have imagined 40 years back that computers would become so pervasive in our lives, both at work and at home. And maybe with all the advances, both on the hardware side in the robotics, and also combining with artificial intelligence and edge computing and the cloud computing, in 10 or 15 years, robots, we might take robots for granted, both at work or at home. And they might become as ubiquitous as your personal computers. And now the product community where we come from, where we're building the end product, we have to overcome several challenges to make it happen. And we have a lot of technologies, and I'm hoping that they're taking notice of this one. So the 2 challenges, one is the physical stack. The adoption of technology into products poses several engineering challenges, especially the form factor, the thermal issues, cost, processing power at the edge, and the reliability of the communications, and so on and so forth. And the other one is the software stack. Now, creating training models requires data, and this is a big challenge, especially in unstructured environments, and especially with small and mid-sized industries. Although we are tackling a small subset of the problems like in warehouses and pick and place or packaging, but there's a huge number of applications that are yet to be tackled. And this is where the data is lacking, and this data has to be created on the fly. And this is where the human-robot interaction becomes even more important. And humans can act as mentors to teach the robots, and then as the data is getting generated, the robots can also keep learning and keep getting better. So for this, we have a paradigm. We have our human-robot interaction platform is based on a paradigm called learn, teach, and learn. So where both the robot and the human is learning, and while you're learning, the human is also teaching the robot. So you don't have to run tons of materials. As I said, you can unpack the robot and you can start using it in 1 hour. And then as we go, as we see more data and we learn more from the task examples, we are also learning both. And then robots can become good augmenters and good collaborators for humans. And I think that's basically what I had to say. Thank you.
Thank you very much, Mr. Vijay. A very, very interesting topic and very, very interesting presentation. And I want to thank you for your time and participation in this AI Summit. In the interest of time, we'll skip questions, but take those offline. So sure. Thank you once again, Mr. Vijay, and we'll move to the next session.
Thank you, Kamal.